Automatic, Addison.
In this tutorial, we will explore advanced object-oriented programming in C++. Okay, let's begin by exploring the use of getter and setter functions in C++ and how they can be applied to robotics projects. Getter and setter functions, also known as accessor and mutator functions, are used to control access to the private data members of a class. Setter functions allow you to modify the values of private data members, while getter functions allow you to retrieve their values. Let's begin by creating an example to demonstrate the use of setter and getter functions in a robotics context. And to begin, we're going to move to the Documents folder, CPP tutorial. And let's open up our code editor, Visual Studio Code, and we'll type in the password. Let's close this out. And to begin, let's create a file called settergetterexample.cpp. New file, setter getter example.cpp. And type the following into the code editor. I'm going to do pound include IOStream. Let's do class robot arm, curly braces, and do public, and let's do void set position, and let's do our X component of the position, our Y component of the position, and our Z component of the position. X equals X, Y equals Y, Z equals Z. Okay, curly braces. Okay, let's go down below. Let's do int get x const, curly braces, return x. And let's do that again. Int get y const, return y. So int get z const, return z. All right, let's go out here, do private int x, y, and z. Closing semicolon. Let's make sure this all looks good. No little red squiggles. And let's type the main function. I'll explain all of this in a second. Let's do robot arm. Let's do arm.set underscore position 10, 20, 30. Stood C out robot arm position. Okay. Arm.get x. Arm.get y. and then arm.get our final one, Z. And then stood inline. Let's go over and to this stood, and let's do return 0 as we always do in C++ and save. So what are we doing here in this complicated code? So in this code, we define a robot arm class with private data members, X, Y, and Z, representing the position of the robotic arm in a 3D space. We provide a setter function, set position, that allows us to set the values of X, Y, and Z simultaneously. We also provide getter functions, get X, get Y, get Z, that allow us to retrieve the individual values of X, Y, and Z, respectively. These getter functions are marked as const, right there, to indicate that they do not modify the object's state. And then in the main function down here, we create a robot arm object named arm. We set its position using the set position function, and then we retrieve and print the position using the getter functions. So now let's run the code. And the output you should see down here is robot arm position 10, 20, and 30. So you should see the robot arm's position printed in the terminal, demonstrating the use of setter and getter functions. This example illustrates how setter and getter functions can be used in robotics projects to control access to the private data members of a class. By providing setter and getter functions, you can ensure that the robot state is modified and accessed in a controlled manner, maintaining the integrity of your robotic system. Okay, moving to our next topic, we're going to learn about static methods in C++ and how they can be employed in robotics projects. Well, now, what's a static method? Static methods, also known as class methods, are functions that belong to the class itself rather than any specific instance of the class. So you can think of static as shared. They can be called directly on the class without the need to create an object of the class. Static methods are static because they are initialized and loaded into memory when the class itself is loaded, remaining fixed at the class level rather than being created with each object instance. Now, unlike instance methods, which are initialized separately for each object instance, static methods stay in one fixed memory location that's shared across all instances of the class. Let's get some practice. We're going to call it static method example.cpp. Example.cpp. And let's write our code. We're going to start with our pound includes, as we always do. Pound include IOStream, and then pound include CMath. And let's create a class called robotutils. Start with public. Static double calculate distance double x1 double let's see here, double y1 double x2 double y2. Save. Okay, and let's go here. All right, let's go here. We're going to go double dx equal to x2 minus x1 double dy is equal to y2 minus y1. And then we're going to return stood square root of dx times dx plus dy times dy. Friendly semicolons at the end there. Add another semicolon, close this out. Looking good, looking good, looking good. And now let's type our main method. Int main double robot1 x is equal to 0.0, robot 1 y is equal to 0.0, and then double robot 2 x is equal to 3.0, and then robot 2 y is equal to 4.0. Double distance is equal to robot utils, calculate distance, and now we need to put in our values. So we're going to do robot 1 x, robot 1 y, robot 2 x, robot 2 y. Semicolon to close that sucker out. And let's do our stood cout distance between robots. Distance stood end L. Save. And down here, we're going to go return 0. How we looking? How we looking? How we looking? Pretty good. No red squiggles, no error messages. Now let's explain the code. So in this code, we define a robot utils class with a static method called calculate distance. This method takes 4 parameters representing the x and y coordinates of 2 points and calculates the Euclidean distance between them. The calculate distance method is marked as static, which means it can be called directly on the robot utils class without the need to create an instance of the class. Now in the main function down here, we define the coordinates of 2 robots, robot 1 and robot 2. We then call the calculate distance method directly on the robot utils class, passing the coordinates of the 2 robots as arguments. Finally, we print the calculated distance right here, line 18. Now, when we run the code, you should see the distance between the 2 robots printed in the terminal, and in my case, that is 5. So by using static methods, you can organize your code more effectively and make certain functions accessible without the need to create objects, and this leads to cleaner and more maintainable code in your robotics projects. Let's explore virtual functions in C++ and how they can be implemented in robotics projects. Virtual functions are a key concept in object-oriented programming that enables polymorphism. They allow derived classes to provide their own implementation of a function that is already defined in the base class. Let's create a C++ file and name it virtual function example.cpp. Virtual function example.cpp. And let's type the following into the code editor. Pound include IOStream. Let's do robot class. And let's do public virtual void move. And let's say stood C out. Robot is moving. Stood end L. Let's just copy all this. I'm going to do this again. And let's call the next class right here wheeled robot. And let's do public robot like that, the colon. And we're going to do under public, we're going to do void. Let's get rid of this virtual here. Void move, and we need to override the standard default function for move, which is defined in the robot class, of which we are inheriting in here. And we're going to say wheeled robot is rolling. Does that look okay? I think it does. Let's do another one. Let's do legged robot. Just copy that, extend it, inherit from the robot. And this is going to be legged robot is moving. We need to copy that and put that there. It's all looking good, looking good, looking good. And let's create let's fix this here, public. Just line it up. Is that lined up? No, needs to be shifted over a little bit. Oops, deleted some stuff. Put that there, align that, public. Okay, and then let's align this curly brace with the class. All right, that's looking good. And now let's do our main method, int main. Do robot asterisk robot1 is equal to new wheeled robot robot2 is equal to new legged robot robot1 move robot2 move delete robot1 delete robot2 return 0. Looking good. So what are we doing in this code? In this code, we define a base class robot with the virtual function move. The move function in the robot class provides the default implementation that prints robot is moving. We then define two derived classes, wheeled robot and legged robot, which inherit from the robot class. Both derived classes override the move function to provide their own specific implementation. So, for example, the wheeled robot class prints out wheeled robot is rolling. You see me rolling. And the legged robot right here, legged robot is moving. Oop, misspelled rolling. Instead of moving, let's say legged robot is walking. That makes more sense. So in the main function, we create pointers to the base class, robot. But we assign them objects of the derived classes, wheeled robot and legged robot. We then call the move function, using these pointers. Now let's run the code. And we've got some problems in here. Says we're missing some stuff here. Type error argument given to delete expected pointer. And what is our problem here? Oh, misspelled. Run it again. There we go. Okay. A little misspelling, a little typo. So now you can see here we have wheeled robot is rolling and legged robot is walking. So you should see the output here of the move function for each robot. And this demonstrates polymorphism through virtual functions. Virtual functions are particularly useful when working with different types of robots or robot components that share a common interface but have varying behaviors. They allow you to write more modular and extensible code, making your robotics projects easier to maintain and expand. Now let's dive into understanding the this pointer in C++, which is important for managing object-oriented programming and robotics applications. The this pointer is an implicit parameter to all non-static members functions, giving a method access to the invoking object's address. Let's start by creating an example that demonstrates how the this pointer can be used to access object members and ensure clarity in the code, especially when parameter names are the same as data member names. We're going to create a new file and we're going to call it robot coordinates.cpp. And type the following into the code editor. We're going to do pound include iostream class robot public. And let's do int x, comma y, robot, int x, comma int y. This x equals x. This y equals y. Void print coordinates. Stood cout coordinates. This x this y. And then let's do stood and del. Put our semicolon out of here. And let's now do our main function at main. Robot, my robot 3, 7. My underscore robot dot print coordinates. then return 0. All good? So what are we doing in this code? In this code, we define a class robot with two data members, X and Y, both integers. The constructor takes two parameters with the same names as the data members. We use the this and then that arrow and then the X, as well as the this and then the arrow and then the Y to assign the value of the parameters to the object's data members, making it clear which variables are being referenced. Now let's run the code. And you can see in the output, we see coordinates 3 and then 7 in the terminal. So this example illustrates how the this pointer helps in referring to the calling object's members, especially in scenarios where local variables or parameters may shadow member names. This is particularly useful in larger robotics projects where such conflicts might arise more frequently. Let's cover the basics of using pointer operators in C++. Understanding pointers is essential for developing efficient robotics applications where you often need to manipulate memory directly for performance and flexibility. Let's get started by creating a practical example that demonstrates the use of pointer operators to handle data effectively. I'm going to create a file and let's call it sensordatapointers.cpp. And type the following into the code editor. We're going to do pound include iostream int main int sensor value equal 100 int pointer sensor value stood cout sensor value ptr stood indel stood cout memory address ptr stood indel. Then ptr equal 200. And then stood cout updated sensor value. We need to pass the value of the sensor value in here. Return 0. Save. All looking good, all looking good. So what are we doing in this code? In this code, we define an integer sensor value and a pointer PTR, which holds the address of sensor value. We use the dereference operator to access and modify the value stored at the memory address the pointer is pointing to. So take a look at what happens when we run the code. So you can see memory address right here, our pointer, memory address, and we have this gobbledygook right here. You see the sensor value, which was just above here, dereferencing. Right here, we are able to extract the value right here. And then this pointer is the actual raw memory address. And then we have updated sensor value right here. We had to dereference this and the pointer and set it to 200. So we had the value of 200. So how does all of this work? A pointer is like giving multiple parts of your program a map to where a single piece of data lives in memory. Instead of making copies, so that's how it works. Imagine copying a huge video feed multiple times versus just pointing to where it exists once. So this is important in robotics, where you're often working with massive amounts of real-time data. You have video feeds, you have sensor arrays, 3D maps, and you need to be efficient with your limited memory, limited RAM, especially on embedded systems that don't have much memory to begin with. So the concept of pointers will come in really handy here. Okay, let's close out that file and let's explore polymorphism in C++, a core concept in object-oriented programming that is important for building flexible and scalable robotic systems. Polymorphism enables us to interact with different types of objects through a common interface, allowing for more generalized and reusable code. I'm going to create a new file called robotactuators.cpp. And let's start. As we always do, pound include IO stream. Base class actuator, public virtual void activate equals 0. So this is our pure virtual function. Need the semicolon. Now our derived class. Public actuator. Let's go over here, public. Let's do an indent. Void activate. Have to override it. Let's do it. Cout. Motor is running. Stood and down. Okay, we're closing it out. Semicolon there. Okay, and let's do another derived class, And let's just copy paste that over here. And let's call this one servo. And let's say this one, servo adjusting position. Let's do here function that demonstrates polymorphism. Void test actuator. Actuator.activate. Do int main motor servo. test, actuator, motor. Test, actuator, servo. Return 0. All looking good. So what are we doing in here? What are we doing in here? So in this case, the test actuator function takes a reference actuator to an actuator object. Using a reference ensures that no copying of the object occurs, which enhances efficiency by saving memory and processing time. It also guarantees that the past object is valid since references cannot be null. It adds a layer of safety to our function. So now let's run the code. And you can see motor is running, followed by servo is adjusting position in the terminal. And this demonstrates polymorphic behavior. By using polymorphism, you can manage various types of robotic components through a unified interface. This simplifies greatly complex software architectures. This concludes our tutorial. Thank you very much, and I'll see you in the next tutorial. Keep building.